So as you put this into your notes, we already have this formula in our notes from before. We just didn't specify it as the definite integral. We just said that was how we calculated the integral. But there's actually different types of integrals. There's the definite integral, which is what we've been using recently because we can actually find it between those values. And there's the indefinite integral here, which you notice is fairly generic. If I start with some function f of x, the indefinite integral is the antiderivative, and it includes the plus c. Now technically I actually could have just written f of x there, because our antiderivative generally includes the c, but I included the plus c there just to help us remember that this is the one where we do include that. Now we're going to practice that idea by finding some various types of integrals here, starting with this one. In this case, I'd like you please to find the indefinite integral of this function. Alright, so in order to do this problem, basically we're just finding the antiderivative like we already know to do. So, I'm going to go through each of these terms up here, and I'm going to find the antiderivative for each. So, for the y cubed, we're using power rule backwards here, so that becomes y to the fourth, and then I multiply that by the reciprocal, so that's going to be 0.25. Now, normally I write 1/4. In this case, I'm not writing 1/4, I'm writing 0.25 just because I got decimals up here. So I generally want to choose either to stick with decimals or stick with fractions. That's not like it's wrong if you wrote 1/4. Alright, then plus my y squared is going to become y cubed. And so then I have to do the 1.8 divided by 3. That's going to give us 0.6. And then minus. And then this y is going to become y squared. And so that means I need to divide the 2.4 by 2. That gives me 1.2. And then this is one of those cases where this is giving us the general antiderivative. That's what our indefinite integral is. And so I want to include the plus c. And then that is it. That's our final answer right there. So now go ahead and find this indefinite integral. A few more layers involved in the process, but I think you got how to do it. Let's find out. First thing you want to do, turn our function here just into an expanded polynomial. So go ahead and multiply all of that out. And so then once you've expanded it, this is what you're really finding the antiderivative of. That's what you're finding the indefinite integral of. And so then this is what you should be looking at when you do the integral. We end up getting 1/6 times v to the 6th plus v to the 4th. I always love it when it cancels out the coefficient exactly. Plus 2v squared. And then we have to remember that plus c hanging on the end. Because when we say indefinite integral, it's the equivalent of saying the most general antiderivative. It's basically saying the same thing there. And so when approaching this one, again, we actually start it the same way as we started that last one. Distribute. So in this case, you're going to multiply that secant t into both of those. So this is what we're really taking the indefinite integral of. It's going to be the indefinite integral of the secant squared t plus the secant tangent of t. When you do this, remember, we're really just taking that indefinite integral of each of those terms individually. And so, in order to do that, we have to say the derivative of what is secant squared? Well, that is tangent. And so that gives me tangent of t. That takes care of the secant squared, because the derivative of tangent is secant squared. Plus, okay, the derivative of what is secant times tangent? That's secant. So then this becomes secant of t, because the derivative of secant is secant tangent. Well?
Plus
We're almost done. Yep, very good. Plus c. Now we're done. Now we have our actual indefinite integral. Nice. Now, this particular problem actually illustrates one kind of general principle, though, at least for the time being. Anytime you see something like this, where we have parentheses in the original problem, think about distributing first. And then anytime we end up with something like this in our problem, where we got like secant squared, or something where we wouldn't necessarily know how to do the antiderivative of it normally, take a look back through those old formulas we have, like the derivatives of trig functions, the derivatives of inverse trig functions, all of those kinds of things, and look for something in there, because there's a lot of odd-looking ones that come up, but we know how to deal with them just because they actually come out of those old notes, out of those old derivative rules. And so you notice in this case we're actually finding the definite integral. But we still start the same way. Start by finding that antiderivative. Alright, so in order to do that, we start by expanding out our function, so I wrote it as f of t, and multiply all that out, and then we can take our antiderivative. Now you notice in this case I did not bother writing in the plus c. That's because I know that I'm taking a definite integral in this case. You could put in the plus c, but you're just going to end up canceling it out by the time you're all done. So we don't need to worry about it. Now that we've done that, now go into the definite integral part. So that means, in other words, you got to figure out what does f of 1 equal, and what does capital F of negative 1 equal. And so here we can see our values that we get for f of 1, capital F of 1 that is, and capital F of negative 1. And then we subtract those to actually evaluate the definite integral. So we do f of 1, capital F of 1 that is, minus capital F of negative 1. And so then we do the 1/12 minus the 1 5/12. And we should get an answer here of a negative 1 1/3. And we're done. So notice the difference though. Indefinite integral leaves you with an equation. It leaves you with a function. It tells you that the indefinite integral equals basically this for the most part. It gets you to that kind of a point. But the definite integral actually tells us the number. And so the indefinite integral gives us something we can work with a little bit more flexibly in some different situations. But the definite integral tells us something definite. It tells us something very concrete, which is that the area under the curve here is a negative 1 1/3. It's actually telling us something about the situation, which is always nice to know.